video is in continuation with the unit 2nd of the DCCN, which is data link layer. Today we are going to discuss our next topic, which is checksum. So in checksum error detection scheme, the data is divided into the k segment in each of m bits. In the sender ends, the segment are added using 1's complement arithmetic to get the sum. The sum is complemented to get the checksum. The checksum segment is sent along with the data segment. So we calculate the sum of the data and then it is sent along with the data. At the receiver end, all received segments are added using 1's complement arithmetic to get the sum. The total sum is complemented. If the result is 0, the received data is accepted, otherwise discarded. So we'll understand, like over here we have our data, a k is equals to 4, m is equals to 8. So sender will convert it, will add these bits, then do it 1's complement, right? Then in the next step it will in the inversion of in the first step, like we have calculated, the sender segment is using 1's complement arithmetic to get the sum, the total complemented sum to get the checksum, right? So here we are performing the sum of all the received data in the one by one. Like we have 4 bytes, so we are adding all the 4 bytes, right? So this is the total sum, and the final is this is the checksum. In the receiver and we will again start calculating, and if the resultant, if the complement is 0 0, then the data is accepted. Next is standardized polynomial code. A polynomial code is a linear code having a set of valid code words that comprises of polynomials divisible by a shorter fixed polynomial is known as generator polynomial. They are used for error detection and correction during the transmission of data as well as storage of the data. The code words, which are essentially bit strings, are represented by polynomials whose coefficients are either 0 or 1. A k-bit word is represented by a polynomial ranging from x power 0 to x power k minus 1. The order of this polynomial is the power of the highest coefficient, that is k minus 1. For example, an 8-bit word 11001101 is represented by the following polynomial of order 7. So we can represent it like over here, the number which is multiplied with the x and raised to some power. Then here it is at the 7th position, like n minus 1 is followed. Here it is at the 8th position, to n minus 1, that is 7. So and so on, we can calculate polynomial for the whole bit. So this is the polynomial representation of 11011101. A polynomial code operation are done by Modulo 2 arithmetic. So Modulo 2 arithmetics are being performed. First is the addition and subtraction. According to the rules, the finite field theory in Modulo 2 arithmetic, addition and subtraction has no carries or the borrow. Thus the both operations are same as the XOR operations, right? So addition and subtraction here are performed using the XOR operation. Multiplication, modulo 2 multiplication is same as the AND operation. So we can perform these operations and easily we can convert any binary number into the polynomial form. So this is the representation. This is an example. Here we have taken, this is the divisor, dividend, and this is the quotient, and this is the remainder. Like we will divide it according to the mathematical process. So all operations can, subtraction, multiplication, division, can be performed easily on the polynomials. Next is error correction method. So here we will discuss some method. First is the Hamming code. Hamming code is a block code that is capable of detecting up to simultaneous bit error and correcting single bit error. In this coding method, the source encodes the message by inserting redundant bit within the message. These redundant bits are extra bit that are generated and inserted at a specific position in the message itself to enable the error detection and the correction. When the destination receives the message, it performs the recalculation to detect errors and find the bit position that has error. Encoding message by Hamming code. So here we will discuss how message is being encoded. The procedure used by the sender to encode the message encompasses the following steps. Step 1. Calculation of the number of redundant bit. Second, positioning the redundant bit. Third, calculating the values of each redundant bit. Once the redundant bit is embedded within the message, this is sent to the user. Calculation of the number of the redundant bit. If the message contains m number of data bits, r number of redundant bits are added to it so that mr is able to indicate at least m plus r plus 1 different states. Here m plus r indicate location of an error in each of m plus r bits position, and one additional state indicates no error. Since r bits can represent 2 power r states, 2 power r states must be at least equal to m plus r plus 1. Thus the following equation should hold. 2 power r should be greater than m plus r plus 1. Positioning the redundant, how they are positioned. Our redundant bits are at bit position of power 2, that is 1, 2, 4, 8, 16, etc. They are referred in the rest of this text as r1, r2, r3, r4 and so on. Step 3 is calculating the value of each redundant bit. The redundant bit or parity bit. A parity bit is an extra bit that makes the number of ones either even or odd. The two types of parities are even parity. Here the total number of bits in the message are made even. And odd parity. Here the total number of bits in the message are made odd. Each redundant bit Ri is calculated as the parity, generally even parity, based upon its bits position. It covers all bits position whose binary representation includes a 1 in the ith position except the position of Ri. Thus R1 is the parity bit for all data bits in position whose binary representation include a 1 in the least significant position excluding 1, 3, 5, 7, 9, 11 and so on. R2 is the parity bit for all data bits in position whose binary representation include a 1 in the position 2 from right except 2, 3, 6, 7, 10, 11 and so on. R3 is the parity bit for all data bits in position whose binary representation include a 1 in the position 3 from right except 4, 5 minus 7, 12 minus 15, 20 minus 30 and so on. Decoding a message in the Hamming code. Once the receiver gets the incoming message, it performs a recalculation to detect the error and correct them. The steps are: the first step is calculation of the number of redundant bits, second is positioning of the redundant bit, parity checking, and fourth is the error correction and the detection. Let's discuss them in detail. Calculation of the number of redundant bits using the same formula as in encoding. The number of redundant bits are ascertained. 2 power r greater than m plus r plus 1, where m is the number of data bits and r is the number of redundant bits. Step 2. Positioning the redundant bits. The r redundant bits placed at bit position of power of 2 is 1, 2, 4, 8, 16, etc. Parity checking. Parity bits are calculated based on the data bits and the redundant bits using the same rule as during generation of C1, C2, C3, C4, etc. Thus C1 parity 1, 3, 5, 7, 9, 11 and so on. C2 parity 2, 3, 6, 7, 10, 11 and so on. C3 4, 7, 12, 15, 20, 23 and so on. Error detection and correction. The last step, the decimal equivalent of the parity bits binary values. Decimal equivalent of the parity bits binary values is calculated. If it is 0, there is no error. Otherwise, the decimal value gives the bit position which has error. For example, C1, C2, C3, C4, 1001. It implies that data bit at position 9 decimal equivalent of 1001 has error. The bit is flipped to get the correct message. So this was all about the Hamming code, how error is detected and corrected. Next method is the CRC, which is cyclic redundancy check. In CRC, a sequence of redundant bit called cyclic redundant bits are appended to the end of the data unit so that resulting data unit becomes exactly divisible by a second predetermined binary number. At the destination, the incoming data unit is divided by the same number. If at this step there is no remainder, the data unit is assumed to be correct and therefore accepted. A remainder indicates the data unit has been damaged in transmit and therefore must be rejected. So this is the diagrammatic representation of the CRC. Now let's understand with the help of the example. Like we have our code, we have our divisor will perform the XOR operation over here, right? So at the whatever will be the remainder will be added to the message, and this code word will be transmitted to the receiver. At the receiver end, it will again divide the code word with the quotient, and if the remainder is 0, that means the received word is the valid word. No error has been transmitted during the transmission. So this was all about the checksum over here. Next we are going to discuss over forward error correction. Forward error correction, FEC, is an error correction technique to detect and correct a limited number of errors in transmitted data without the need for the retransmission. In this method, the sender sends a redundant error correcting codes along the data frame. The receiver performs necessary checks based upon the additional redundant bit. If it finds the data is free from errors, it executes the error correcting code that generates the actual frame. It then removes the redundant bit from before passing the message to the upper layer. Advantage and disadvantage: because FEC does not require handshaking between the source and destination, it can be used for the broadcasting of data to many destinations simultaneously for the single source. Another advantage is that FEC save bandwidth required for retransmission, so it is used in real-time system. Its main limitation is that if there are too many errors, the frame need to be retransmitted. So error correcting codes for the FEC. Error correcting codes for the forward error correction can be broadly categorized into two types, namely block codes and the convolution code. Block code: the message is divided into fixed size blocks, bits to which redundant bits are added for error correction. Convolutional code: the message comprises of data stream of arbitrary length and parity symbol are generated by sliding application of Boolean function to the data stream. There are the four popular used error correction code. Having code: it is the block code that is capable of detecting up to 2 simultaneous bit errors and correcting up to single bit. Binary convolution: here encoder encompasses an input sequence of bits of arbitrary length and generate a sequence of output bits. Next is read-Solomon code. They are block codes that are capable of correcting worst error in the received data block. Last is the low density parity check code. It is the block code specified by the parity check matrix containing a low density of ones. They are suitable for the large blocks in the very noisy channel. So this was all about the forward error correcting method. So we'll discontinue over here only. In the next session we'll continue with the next topic. Thank you so much.